Hi, everyone. Welcome to the videos for Lecture 11 of Privacy in Machine Learning and Statistics. So today, we're going to start a small unit on optimization that will be a lead-in to a bigger unit on query release and generation of synthetic data. So the optimization problems we're going to be looking at it's really a family of problems that come up a lot in when we're fitting models in machine learning and statistics. So a common type of problem is that given the data, we define a loss function that we would like to optimize, we would like to minimize. Okay, so what's an example of that? Well, let's look at the mean. The mean of a bunch of points x1 through xn that are all real numbers. We can think of the mean as computed as a sum. It's of course this quantity. But it turns out it's also the following quantity. It is the minimizer over all the real line. It is the number that minimizes the following function. It's the number that minimizes the sum from I equals 1 to n of xi minus w squared. And for reasons that will be, for convenience later, we'll often define this type of function with a 1 over n out front to make it more of an average than a sum. Okay, so you may or may not have seen this before, but you can figure this out. You can verify for yourself that if you take the derivative of this thing here, which I'll call this a loss function of w. If you take the derivative of L at W, you'll see that the only way to make that derivative 0 is to set W to be the actual mean of the data set. And because L itself is differentiable and increasing as you go away from the mean in either direction, it increases to infinity in both directions. There's only one place where the derivative can be 0, and so that place has to be a minimizer. The median can also be written in this way. So the median of a bunch of data points of x1 through xn, it can be written as the minimizer. So the median of this data set x is the minimizer of the following function. So you may not have seen this notation before, but just to explain what this means, this argmin expression, it means that I want to return the value that minimizes the expression that follows. So like if I were to write minimum of that, I would want like the actual minimum value of the expression. So like the minimum of like this loss function up here would be some kind of approximation to the variance of the x's. But when I write argmin, what I'm saying is I want the quantity, I want the value of w that minimizes this expression. So let's do one more example. So let's say linear regression. That's another one that maybe you've seen before. So here my inputs are not real numbers. They're actually pairs of vectors and numbers. So the data are pairs like xi, yi, where xi is a d-dimensional real vector and yi is a real number. And the loss function that we care to we minimize when we're doing ordinary least squares linear regression is following. So we're interested in minimizing over w in r to the d. So this is the number of parameters that we, number of parameters is equal to the dimensionality of the data vectors xi, or sometimes dimensionality plus 1 if we want to add a constant term. And the loss function looks like this. I want to see if the yi's are well approximated by the inner product of xi and w. So I want to find a w such that the inner product of w with the xi's approximates each of the yi's as well as possible. And so what I'll do is I'll, or a typical way to set this up is to minimize the sum of these squared errors. So again, the output of the regression coefficients output by typical ordinary least squares linear regression are the coefficients of the vector w, whose inner product with the xi's is as close in this sense as possible to the yi's. Okay, so these are just 3 examples. These are, these are 3 examples. They have in common that they have various things in common, but notice that the loss function is a sum. With 1 term per data point. Okay. These particular loss functions are actually convex, although we certainly don't always have that. There are lots of loss functions people optimize in, every day that are not convex, and that's can be quite a challenge, although we'll be talking about convex optimization quite a bit next lecture. And so the other thing these have in common is that the feasible set doesn't depend on the data. In fact, in this case, the feasible set is all of r to the d, but that we won't always have. But one important thing is that the set over which we're optimizing is not data dependent. Okay, that's going to be important for us because it's going to simplify the kinds of things we have to worry about when we're designing a differentially private algorithm. Okay, so what we'd like to do is write down a sort of an abstract problem that captures all the examples we've seen plus a bunch more. Okay, so that's what we're going to do. So we'll say that, so we'll introduce some terms. So decomposable loss is a loss function that's made up of a sum of terms like this, 1 per data point. So, so we'll say that L of W X, where X is a data set, is decomposable if it can be written in this form as the sum from 1 to I equals n of some I equals 1 to n of some little loss function, L of W xi, that's been applied to each data set individually. So these are called individual losses. And then sometimes we'll add another term here. We'll call it, I'll just call it like lambda W. This is a regularizer. It's usually used to sort of help us select for a particular type of solution, like to penalize very complicated solutions, or usually like long vectors, and vectors with big entries. All right, and the problem that we're going to be looking at is typically called the empirical risk problem. Empirical risk problem. So given this little loss function L, well, I mean the ERM, empirical risk minimization, makes sense even for non-decomposable losses, but for simplicity, we're going to stick to decomposable losses today. So we specify this little function L, and we we specify a set C called the feasible set. This is the set over which we're going to be optimizing. These are the set of acceptable vectors W. And optionally the regularizer, but I'll leave that out for now. And what we want to, our goal, and so we're given these things and a data set X. So a data set X1 through Xn in some universe to the n. And here the little loss function takes as input an element of C and an element of the universe, and outputs a real number. And the idea is that we want to, we want to find a W that makes this loss function as small as possible. So we want to find W hat such that the loss at W hat minus the, and then we want this W hat to be to satisfy our constraints. So sometimes C is called the constraint set because it encodes like natural constraints on the parameter vector. Like for example, maybe the entries are supposed to be non-negative, or maybe the norm of the parameter vector is supposed to be bounded by some given constant. So we're going to compare the kind of criterion we're going to use is that we're going to compare the loss of the thing we found to the minimum possible loss we could have gotten on the data set. Okay, so this is our problem. So what we're going to see are a number of algorithms that are differentially private and that solve this type of problem under various assumptions on these little loss functions and the constraint set and so on. So in some sense, this is a special case of the selection, the kind of big family of selection problems we saw with the exponential mechanism. Because you could think of this, just like with that selection setup, there was some sort of set of items we cared about. That would be the feasible set, and we wanted to find the best one among them according to some score function. And this is like the loss function is like a negative score function. But we're going to be talking about sort of continuous settings where the set C is, capture the thing we're looking for, W, is a vector of real numbers, and the set C is like a nice set of real numbers, like maybe a convex ball or something like that, like everything within a certain distance of the origin or some, relatively nice set like that. And so that's going to lead us to a different sort of set of algorithmic techniques that we'll be getting into today and tomorrow and the next lecture, and then sort of indirectly over the next few weeks. Okay. So this is called, this problem is called the empirical risk minimization problem because we're minimizing a function, the thing we're worried about is sort of the loss on our data, the data we have, X. Okay. In a lot of statistical settings and machine learning settings, ultimately, we're actually going to be worried about something slightly different. So sometimes people will distinguish what's called the population loss from empirical loss or empirical risk. Risk and loss here are used more or less as synonyms. So if there were, with this, in this perspective, what we do is we suppose that that the data we see are drawn IID from some population, are drawn IID from a distribution P called the population. Okay. And then once we suppose this, even if we don't know this distribution, one can imagine, one can posit that it exists, and you can still define a population level loss. So you can define the population loss, which I'll call like the loss of W at P rather than at the data set. And I can think of this as the loss I would expect for W if I were to get a fresh sample like X prime drawn from P, and I were to evaluate the loss on X prime. Okay, so this population loss is defined with respect to this unknown distribution. That's different from defining it with respect to the data, which is what we did up here. Okay. And so remarkably, in many settings, we can, even though we don't know the distribution P, we can come up with bounds on the population risk. So the population risk is the excess population risk. So excess population risk, that's like if I have an estimator W, I will measure its quality by how much worse it is, or I'll measure how, its badness, its error, by how much worse it is than the best parameter vector for the population as a whole. So often we can bound this population risk. And we'll talk about that distinction between empirical risk and population risk, and what kind of techniques allow us to go between them. But just to tie this into stuff you might have heard before, the difference between the empirical risk of my estimate, if I come up with some W hat, the difference between the empirical risk, which I know, and the population risk, which I don't know, this is called the generalization error of my method, of my particular estimator, or particular W hat. So this is a measure of how misrepresentative the data is of the population for this particular parameter vector. And there are some really fascinating connections between differential privacy and generalization error, and that we'll touch on later in the course. So often, often we can sort of bound this population risk. Often we measure it using a holdout data set or cross validation. And again, we'll talk about that. But for now, we're going to kind of set this aside and really focus on the empirical risk. Okay, so that's really what we're going to be concerned with today and next lecture. Might be useful to go through just a few more examples. So another example that's kind of instructive are what are called support vector machines. So here the idea is you're trying to classify points. You're trying to suppose you've got points from two different classes, and you're trying to find a hyperplane that is, in this case, in 2 dimensions, just a line, but in general, kind of something that's defined as the orthogonal, the set of things orthogonal to some vector passing through some point. You're trying to find a hyperplane that separates these points as well as possible. Okay, and so if I use W to denote the orthogonal vector for my subspace, and if I include a constant term in W, I can basically assume that it passes through the origin, and that's fine. Then a support vector machine is an algorithm where the inputs are pairs xi, yi, so they're real vectors. Each one comes with a binary label in the most basic version. So that label is like -1 or +1. And the thing we're minimizing, so the loss function we care about, so it's the sum from 1 to n of 1 minus this seemingly funny function. So I'll write it out and then explain where it comes from. So this is a function that it has a regularizer. In this case, the regularizer is some multiple lambda times the norm squared of the parameter vector, and that helps us select for kind of nice hyperplanes that have relatively small coefficients. And then the right way to think about what's going on in the middle here is that the binary prediction made by this algorithm on input x is the right way to think of it is as the sign of the inner product of W and xi. So that prediction is correct if and only if yi, which is 1 or -1, times this inner product is greater than 0. Okay. Now, what the idea of this algorithm is that rather than just putting like in the loss function here some kind of misclassification term, which would be like 1 or 0, where 1 if the classifier does the classification correctly and 0 otherwise. The idea is to replace that misclassification error with some more continuous proxy for the misclassification. So the so-called misclassification loss would be like 0 if if the prediction is correct, and 1 if otherwise. So like if you were to plot, yi times wxi, it would be the, true misclassification error would look like this. But instead, what we're doing is we're replacing this true misclassification error with a kind of a different function that is, first of all, it's continuous, so we can do things like use derivatives, and they actually give us information. And secondly, it's convex, which means that it gives that opens up a whole other set of algorithmic tools that we'll talk about. Okay, so this is another example of a decomposable loss function that we'd like to minimize. It's actually a very commonly used algorithm in settings where you can find a linear classifier, where there's a good linear classifier to separate the data. This algorithm actually does not so badly. And it illustrates this interesting idea of taking a kind of non-continuous, non-differentiable misclassification error and replacing it with this more continuous object. Now, historically, the reason people have done that is basically for computational reasons. These continuous functions are easier to work with because they have gradients, because they're convex. But actually, it turns out this shift to this continuous setting is actually going to make things much easier for some of the algorithms we want to run, and it'll actually make it easier to design private algorithms, differentially private algorithms, as we'll see. All right. We can't not mention another huge example of decomposable loss functions. So those are the loss functions that are optimized in the training of deep neural networks. So like also decomposable. I'm not going to spend a bunch of time on that, but again, it's the same setting. You've got a long vector of parameters that somehow describe the behavior of the network, and a loss function that penalizes incorrect behavior, whatever that incorrect means in your setting. And again, the same set of tools that apply to all these classic statistical problems also apply, by and large, to this setting of deep neural nets. Okay, so we've got a class of problems. Let's think about how we might go about designing differentially private algorithms for those problems. Okay, so our starting point is going to be to start to identify what kinds of assumptions we could make on the problem that'll make it amenable to privacy. So maybe the first observation is that we're going to have to somehow limit the influence of individual data points on the big loss function L. So for example, if I could go from a loss function that looks sort of like this, if I could add one data point and wind up with a loss function that looks, totally different, like that, then it's going to be very hard to come up with a differentially private algorithm. In particular, there's no solution for like the data set, the loss function on the right-hand side that's also a good solution for the data set on the left-hand side, and vice versa. So I need some way, so this is like, bad. if we wind up in this situation. So we need some way to limit how much each data point affects things. So there are a couple of typical assumptions that people look at. So the one is that the first one I'll call the bounded loss assumption. So we'll say L is the little loss function, right? It takes a parameter vector and a data point, and it produces a real number. So we'll say it's like delta bounded if it only produces values between 0 and delta. Okay. Or more generally, if it only produces values in a small range, it doesn't really matter that it's between, like that it's includes 0, but because that doesn't really change anything. So notice this is sort of morally, this is more or less the same as requiring that the loss function, the overall loss function L, have low sensitivity for each value of W. Okay, because notice that if I change, so just as a corollary of this, if X and X prime are neighboring data sets, then if I look at how the loss function changes between X and X prime, that's at most delta over n. Okay, so that's one way to measure, to kind of limit the influence of any one point, and that actually is a pretty good one that'll allow us to get at least a handle on differentially private algorithms. Another really useful one is going to be to look at what are called Lipschitz loss functions. So, or what are the full way of saying it is a Lipschitz continuous loss function. So it's a notion of continuity that was named after some mathematician. The idea is that a function is Lipschitz if it's not only continuous, but if the slope at the rate at which it changes, so the gradient, if it has one, is bounded everywhere in the domain of the function by some constant. Okay, so sorry about that. We'll say L is G Lipschitz if for all points in the domain and for all X in X, if I take if I fix X, so we don't know that we're always going to be working with vectors that are real, with W's that are real vectors. The data points X, they can be whatever, they can be anything. They could be like tax forms or something. So we're not going to generally be taking derivatives with respect to X. We're only going to be taking derivatives with respect to this parameter W that we're optimizing, because that's the thing we're trying to move around and find the right value for. So so this is the gradient with respect to W. So one way to define Lipschitzness is to say, well, my function should vary slowly. And so like I could ask that the norm of the loss function of the gradient, the 2 norm of the gradient, be less than G everywhere. Okay, so that's like in one dimension, that's sort of like saying, well, the slope can be negative, it can be positive, and it can vary, but it's sort of always between 0 and 1. So if I look at sort of a line of slope 1, it's never going faster than that. It's never growing or shrinking faster than that, and it's never growing or shrinking faster than the slope of like -1. So this is an example on the right. That's an example of like a 1 Lipschitz function. In general, we've just got some parameter g that measures like how big the gradients can get. So the only problem with the definition as I've written it is that it requires the loss function to be itself differentiable. And if you think of like some of the loss functions we talked about earlier, like the one that defines the median or the one that define the support vector machine, they're not differentiable everywhere. They have these points where the derivative doesn't exist. Or in higher dimensional space, they have like entire lines where the derivative doesn't exist. So what we'll do is we'll define the more general definition is the following. We actually ask that for all u and w in C. So this is sort of like actually what we really want. For all u and w in the constraint set, and for all x in the universe, the difference between the loss at w and the loss at at u that should be bounded by g times the distance between u and w. Okay, so this is actually our definition of a Lipschitz loss function. And so this will allow us to handle non-differentiable functions nicely. And so, for example, if we look at the loss function defined by the mean, so that, remember that the loss function there that's in 1 dimension, the loss function was w minus x squared. So the derivative of this thing is with respect to w, right, is 2 times w minus x. So this is going to be Lipschitz on as long as x and when both the data universe x and the constraint set C are bounded. As long as there's sort of like the numbers can't get very big. If the numbers can get big, then all bets are off. Right? If they can get very far apart from each other, if w minus x can get big, you can get in trouble. If I look at the median, the thing we're looking at was the absolute value function, right? So that one looks like, so here's like x, and you've got, it looks like that. So the derivative with respect to w, this is always either +1 or -1, right? So, so this thing is always 1 Lipschitz. Take another example as the SVM. So with the SVM, this is like we're now in higher dimensions. So w is a vector, x is a vector. So remember the loss function there was like 1 minus y times the inner product of w and x. And then what we do is we take the positive part of that. So like if it's negative or 0, this loss is 0, and if it's if it's positive, it's just whatever the argument is. So if I take the gradient of this thing, so maybe it's good to remember our chain rule from calculus. So the gradient, again, with respect to W of the loss function at the point at W is, so it's going to be the derivative of the outer function. So that'll be the derivative with respect to its argument of this function, like 1 minus t plus, evaluated at t equals the inner product. And it'll be, by the chain rule, it'll be that thing times the derivative with respect, the gradient with respect to W of the inner product, Wx, and that actually is just the vector x. So this thing is always either -1 or 0. And this is, again, small only if this is bounded, like only if the universe, if and only if the universe X is bounded. Okay. And this sort of thing where the loss functions we care about are Lipschitz only if the data is kind of not too crazily behaved. That's a pretty common situation to be in, and as a result, like we'll talk about it when we get there. But like it's often the case that one has to somehow constrain the data in the data set so that to remove any like really big vectors that would like unduly have a lot of like undue influence on the outcome, on the actual execution of the algorithm. Okay, so again, this was, I managed to write down this derivative using the chain rule. And if it's been a while since you saw that, maybe you want to refresh your memory on how the chain rule works, because it's a good thing to have around. Good, tool to have in your toolbox. Okay, so we've got two kinds of limitations we're looking at. We've got, bounded loss and Lipschitz loss. And there are some others that come up when we're analyzing differentially private algorithms, but these are really the most common for the algorithm these are the common requirements for the algorithms to be differentially private. We'll see how to use bounded loss for privacy today, and then we'll see how to use the Lipschitz loss for privacy next lecture.